Hi guys, let's talk about calorimetry today. So the term calorimetry refers to the precise measurement of heat flow either into or out of a system. And remember that system is usually a term that we use for the thing that we are interested in. Now, calorimetry is commonly used to experimentally determine the specific heat of a substance. And it is based upon two premises. The first being that heat released by the system must be equal to the heat absorbed by its surroundings. And that is because of the law of conservation of energy, which says that energy is neither created nor destroyed, but it does change and it does move. Okay. So, mathematically speaking, this idea of the energy of the system has to equal the energy of the surroundings can be written as the Q of the system is equal to the opposite Q of surroundings, where we're using this negative sign to refer to opposite. To break that down further, if you remember, our heat equation is Q is equal to mc delta T. So if I substitute that in for Q, that would mean that the mass of my system times the specific heat of my system times the change in temperature of the system, therefore must be equal to the opposite of the mass of surroundings times specific heat of the surroundings times the change in temperature of the surroundings. Now, a lot of times we use water as the surroundings. So a calorimeter is a device in which we can place a known amount of water, in other words, a known mass of water, and we can take its temperature to find the initial temperature. And then, because we know the specific heat of liquid water is 4.18 joules per gram degree Celsius, we can plug that in and then find the specific heat of our substance or our system. Because our system is going to be something that we can measure its mass, and we can also take its initial and final temperatures. Now, the interesting thing about calorimetry is that both the system and the surroundings will have the same final temperature because heat flows from an area of higher temperature to an area of lower temperature. And it stops flowing when the two things have the same temperature. So, knowing that, let's take a look at an example and break it apart. So, a 28.2 gram sample of nickel is heated to 99.8 degrees Celsius, and then it is placed in a calorimeter containing 150.0 grams of water at a temperature of 23.5 degrees Celsius. After the metal cools, the final temperature of both the metal and the water is 25.0 degrees Celsius, and we are going to be calculating the specific heat of nickel. So, if you remember back to when we talked about heat calculations and using the heat equation, Q equals mc delta T, I mentioned then that we should start with a list of givens. And this can be really important for calorimetry problems because we have so many different values. And we can actually break these up into values for the metal or the system and values for the water, which is going to be our surroundings. Okay. So, metal and water. We know that the mass of the metal is 28.2 grams. So the mass of the metal is 28.2 grams. I also know that my initial temperature of the metal is 99.8 degrees Celsius because it says this is the temperature the metal was heated to. So my initial temperature of the metal is given as 99.8 degrees Celsius. Now my final temperature of the metal is 25.0 degrees Celsius. And that is all I know about the metal. So if I read through and list out what I know about the water, I am told that the water's mass is 150.0 grams. And I'm told that its initial temperature was 23.5 degrees Celsius. And the final temperature is the same 25.0 degrees Celsius. So with calorimetry, you're always going to see this happen, that the final temperature is going to be the same for both things. Now, as always, I know that the specific heat of liquid water is 4.18 joules per gram degrees Celsius. So even though it doesn't explicitly tell me that here in the problem, that is something that I am always able to know. So since I have a final and initial temperature, I can go ahead and calculate delta T, save myself a little bit of trouble. So delta T is always final minus initial. So the delta T of the metal is going to be 25.0 minus 99.8 to give me a negative 74.8 degrees Celsius. And that negative sign makes sense because the metal is cooling down. We are losing heat. So negative makes sense there. The delta T for the water, on the other hand, is 25.0 minus 23.5, 1.5 degrees Celsius. The water heated up, so it makes sense that the delta T is positive here. So now that I have everything listed out, I'm ready to plug in to this formula. And if I want to save myself a little bit more time, considering that I am ultimately trying to solve for the specific heat of the metal, which we are thinking of as the system. If I want to rearrange this equation to solve for the C of the system, then that equation rearranges to give me the specific heat of the metal is going to be the opposite of the mass of the water times the specific heat of the water times the delta T of the water divided by the mass of the metal times the delta T of the metal. So now I can plug in my values and solve for C of the metal. So the mass of the water was given as 150.0 grams times the specific heat of the water, 4.18 joules per gram degree Celsius, times our delta T of the water, which we found to be 1.5 degrees Celsius. I'm going to divide all of that by the mass of the water, 28.2 grams, times the delta T of the metal, the mass of the metal, 28.2 grams, times the delta T of the metal, negative 74.8 degrees Celsius. Now, before we even calculate, we can see that a couple of things are going to happen. Okay. Down here, when we multiply these two values together, it's going to be negative because we're taking a negative times a positive. But that is why it's so important to remember that this is the opposite of this value. Because when you take a negative divided by a negative, that's going to give us a positive. So it's very important to not forget that this top part, you take the opposite of it. The other thing that happens is with our units. So when we multiply these three values together, grams is going to cancel out, and so is degrees Celsius along the top. When I multiply these two things together, nothing cancels out, so I end up keeping both units, grams, degrees Celsius. And that is how we end up with the final unit of specific heat here as joules over grams, degrees Celsius. And taking a look at my units will ultimately help me determine if I have set up my problem correctly. Because if my units don't work themselves out to make sense for what it is that I'm solving for, I've done something wrong. But here, it does make sense to end up with joules over grams degrees Celsius because that is one of our units of specific heat. So the only thing left is to calculate our value. So the opposite of 150.0 times 4.18 times 1.5, close those parentheses, and then we're going to divide that by 28.2 times negative 74.8, close those parentheses, 0.4458, lots and lots of decimal places. So if we look at our sig figs, then our smallest number of sig figs here would be 2 from the 1.5 degrees Celsius here. So I'm going to round this to 2 sig figs, 0.45 joules per gram degrees Celsius. And that will be our final answer. The specific heat of nickel calculated to be 0.45 joules per gram degrees Celsius. Let's look at another example. So in a calorimeter, 100.0 grams of water and 100.0 grams of HBr are mixed. The HBr had an initial temperature of 44.6 degrees Celsius, and the water was originally at 24.6 degrees Celsius. After a few moments, the temperature of both substances is 31.3 degrees Celsius. So, first thing that I want to think about is, was this process exothermic or endothermic for the HBr? Well, if I look at the initial temperature of the HBr, we were initially at 44.6 degrees. And we ended up at 31.3 degrees. So we have a decrease in temperature, which means that we must have lost heat energy. And anytime heat energy is lost or released, that is an exothermic process. So for the HBr, this must be exothermic because temperature decreased. and that means that heat energy was lost. The follow-up question wants us to calculate the specific heat of our HBr. So once again, we're going to make a list. What do we know about the HBr? And what do we know about water? We know that our mass of water is 100.0 grams. And our mass of HBr is also 100.0 grams. The initial temperature of our HBr is 44.6 degrees Celsius. The initial temperature of our water was 24.6 degrees Celsius. The final temperature of both the HBr and the water, 31.3 degrees Celsius. And as always, we know that the specific heat of water is 4.18 joules per gram degrees Celsius as a liquid. So I can find my delta T of the HBr. So final 31.3 minus initial 44.6. Negative 13.3 degrees. I can do the same. I can find my delta H of the water. So final minus initial, 31.3 minus 24.6, excuse me. 6.7 degrees Celsius. So I'm going to be using the same equation that we did before. So the specific heat of HBr is going to be found by taking the opposite of the mass of the water, 100.0 grams, times the specific heat of water, 4.18 joules per gram degree Celsius, times the delta T of water, which we found to be 6.7 degrees Celsius. Excuse me. We're going to divide that by the mass of the HBr, 100.0 grams, times the delta T of the HBr we found to be negative 13.3 degrees Celsius. And just like before, our units work out. Grams and degrees Celsius cancel along the top, leaving us with just joules up top, and both grams degrees Celsius on the bottom. Okay. So let's calculate the opposite of 100.0 times 4.18 times 6.7 divided by 100.0 times negative 13.3. And if we look at our sig figs, we want to go with the smallest number of sig figs since we are multiplying and dividing. So that looks like 2 based upon the 6.7. So 2.1 joules per gram degrees Celsius will be our final answer as the specific heat of HBr.